This video and content relating to this video has been approved by Dan Sheckman. Hello and welcome. In today's video, we'll be discussing the particle in a 3D box and how it can be modelled using Python. Let's begin by asking the question of why are we even bothering to model a particle in a box? Well, to begin with, it provides us with a simplistic representation of a very abstract topic, and it helps us illustrate the difference between classical and quantum systems. And there's no need for complicated mathematics to provide insight into quantum chemistry. And it helps us derive the reason for why energy must be quantized. And of course, because Fran told us to. So, to define our wave function for a 3D box, we must first look at the time-independent Schrödinger equation and the limitations that we pose onto that wave function. The limitations are that it must not be infinite over a finite region, each value must be single valued, and our wave function must be continuous. By this means, we can use a sine function, as shown down here, where we have our x and our y, and we just times these two wave functions together with this a value, the normalization constant. The entire purpose of the wave function is to predict the probability of finding an electron in a space. Therefore, the probability must equal 1 when we square the wave function. Right now, it means that we need to normalize this wave function. This is achieved by integrating the wave function between two limits and then rearranging to find a, as we see down here. To start writing my code, I started by importing these three functions, which allow us to use mathematical formulae and functions, plot our graphs, and then plot them in 3D. I started by assigning the variables n, which was our quantum number, l, which is the length of our box, and then x and y, which are the values that are going to go into our wave function, and they're linearly spaced values from 0 to l in 100 equally spaced intervals. And we've got a, which was our normalization constant that we derived previously. And down here, you can see how those variables get saved. So now using the variables that we've already defined, we're going to actually make the values for our wave function in our z coordinate using this def function, which is basically just a function that we're setting ourselves so that we don't have to repeat this same line of code over and over again. And we're going to return that variable. If you look at actually running it, we've got this x and y coordinate here, and then it's spitting out this value. In this case, it's just a single number, but in our actual code, it's going to be an array. Using the variables that we've just defined, we can now make our value for our z-axis, which would be our wave function. So first we need to make a mesh grid, which is basically a matrix seen down below here, of x and y. And then what we do is for every value of x and y, we then use the function that we've previously defined and get this array psi, but we need to reshape the variable because we've currently got 10,000 values in there. We need to get 100 values so that it matches our x and y, and we can just simply do this by reshaping the variable. Now all that's left to do is actually plot our particle in our box, which is done easily by this 3 lines of code here, which plot x, y and psi together in a 3D projection, and we're just going to label our axes and give our graph a title. Now it's time to have a look at our waves. So here they are, our 3 graphs for our particle in a 2D box, with our quantum number 1, 2 and 3. And what you can see is that as we increase the quantum number, you get more nodes and you start to get negative values, and you can start to see that these first two start to look like s orbitals and this one looking kind of like a p orbital. Now it's all left to do is to find the probability densities. And finally, here are our last set of graphs which are showing the probability density, which was achieved by just squaring our wave function which was the psi value. And here you can see some small differences where the negative values have now become positive, and that you can see that the probability of finding an electron is closer to the center of these peaks rather than off to the sides of the box. So those were all of our graphs plotted using Python. Thanks for listening, and thanks for watching. Leave a like, subscribe, and hit that bell notification to stay tuned for future content. See you in the next one.